Can you hear me?
Yeah, I can hear you.
Okay, cool. Wow, you're still in school uniform. You went to school this morning.
Yeah.
You got exam today.
Right. This Monday start.
Sorry?
This Monday start.
All right. Okay, cool. All right. Suppose that your final written paper will be sometime in early November, right? But
Yeah.
Okay.
6.
With biochemistry, it's very simple. Because there's no written exam, they will let you know very early. First of all, they let you know the earliest if you're rejected straight away. So there will be early November. Don't be disheartened or whatever if you hear that in the middle of your exam, but it's part of the journey. Secondly, what's the second thing I was gonna say? If you don't hear until mid-November, that means you might have gone through the second round selection, and then they will filter, and then they will reject a couple more people because they have a baseline. So
Yeah.
people's O level, and then people predictions, and then their forecast, and then they can only interview so many people. Okay, but anyway, you done all you can with your personal statement, and then the next best thing for you is to get a AAA star to ensure that you're not losing anything at all, just in case. Yeah, okay. So AAA star should be in your mind, and you should enjoy your exam in the sense that you're confident enough going in, and you should be good enough to get the AAA star required for minimal entry into Oxbridge. Yeah, I know it doesn't require AAA star, but that's why you need to keep your mind open so that anything is possible. Yeah. Okay, are you ready to start?
Yeah.
Cool. All right. What do you know something about ethane and butane? Can you draw for me an ethane molecule and a butane molecule? So both are alkane, yeah?
Yeah.
So as you notice, I don't really cover a lot of biology with you because I'm not a biologist. But at some point, if you do get an interview, I'll arrange for a biologist to chat with you.
Yeah.
Okay, cool. All right. So you can rotate about a single bond, right?
What's that? Sorry.
You can rotate about a carbon-carbon single bond, can you? Okay. Imagine if you have that ethane molecule, what's the geometry at each of the carbon in ethane? What's the shape?
109.5 degrees.
So it's not exactly 90 degrees as you have drawn, right? Okay.
Yeah.
Now I want you to imagine if you have that molecule, if you have an ethane molecule, so there are 109 like that. So it's like 3 of them like that, and then 3 of them like that. So you have that carbon-carbon single bond in between. Can you imagine looking down that carbon-carbon single bond? So if you have that molecule there, what you have drawn, look in your vision, look across the carbon-carbon single bond. Okay? How would it look like to you? Can you project it onto a paper? How would it look like to you? If you look, so basically your eye is looking onto the carbon-carbon single bond. How would the rest of the hydrogen look like to you? So there are 2 carbon. So one of the carbon must be closer to you, one of the carbon must be further away from you. How would it look like to you? So this is an artistic representation. Like how would you draw it on paper? Can you imagine it?
Wait. I would see it as 1 carbon only.
Yeah. How would the hydrogen look like?
So 3D. The hydrogen will be 3D. Okay. For me, I guess I would only see a 1 carbon.
Okay. So you're saying you're looking at it like that, but that is still how you're looking at it on the surface, you see. What I want is for you to look onto the carbon-carbon bond. So actually, like, you can think about it like that, can you not?
Oh, okay. Wait.
It's the same representation as what you have drawn.
Yeah.
But imagine I've just tilted it sideways. Of course, this is not, I haven't drawn in the wedges and things. This is just another way of representing a molecule which you are not used to at levels. Now I want you to just, can you draw this on your paper? Can you draw this somewhere on your paper? I mean, basically you just tilt it sideways so that you can see what is in front and what's at the back. You got it?
Yeah.
Okay. So the next thing is, what if your eye is looking down the carbon-carbon bond? So your eye is looking down on there. So yeah, okay. So how would it look like to you? I'll show you what I mean. If I have this carbon, so I know the carbon is overlapped by the carbon. Okay. So I have something in front. So I will have a hydrogen in front. I will have something that look like that, right? Because I'm looking down there. Can you imagine how the hydrogen at the back would look like? Can you just kind of like complete this diagram? So this is in front. So the back would be somewhere at the back, but how would it look relative to the one in front? Do you understand the question?
Yeah. How will look at the back? Wait, so
yeah.
I connect. Do I connect the back of that one?
No, you're looking. Your eye is here. You're looking at this carbon. So this is the carbon. This is the carbon. This is the carbon in front, and the carbon at the back is being overlapped by the carbon in front because you are looking down this carbon. You are not looking on the plane. You are looking along the carbon bond.
Yeah.
You are looking along the carbon bond. So how would the protons at the back? How would the hydrogen at the back look like?
Oh, okay.
Just draw what you think, and then we'll move on from there.
You mean if I look from the back, is it?
No, you look from here.
Oh, if I look from here.
You could look from the front or you could look from the back. It doesn't matter. But wherever you look, if you look from here, this is your front. If you look from here, this is your front. If this is front, this is your back. If this is your front, this is your back. It's just a matter of perspective. Where is your eye?
Okay.
So you have the molecule on your paper. Just imagine looking down the carbon bond. Okay. Just draw what you think first, and then I'll guide you from there.
What I'm thinking is, I might be able to see the hydrogen if they rotate in a different direction.
Okay, cool. So you have so you have connected it to the middle, but actually you won't be able to see the carbon in the middle because it's being overlapped by the carbon in front. So what you will see is you are absolutely right. So what you have drawn is this, right?
Yeah.
The one in front, what you can see. The one at the back is something like that. All right.
Yeah.
And what you have drawn is something like this, where the hydrogen is just perfectly sitting in between happily. Okay, and that's fine. And one thing you notice is that you can rotate along this carbon-carbon bond, right?
Yeah.
Okay. The next thing is, I'm gonna tell you something. If I label this angle, if I have one of them fixed, if I have the one in front fixed like this, if I fix the CH3 in front, I rotate along the carbon-carbon bond, I can get this hydrogen that this and this overlap because they are like, parallel to each other. So essentially theta will be 0 because they overlap each other, right?
Yeah.
Okay. Now I want you to think from the position where this hydrogen at the back overlap this hydrogen in front, there's theta equal to 0.
Yeah.
Can you rotate this carbon-carbon bond so that this CH3 will rotate around. Yeah.
Sorry, I didn't understand the question.
Okay, let me show you again. So you understand that this is my theta. My theta is the angle that the hydrogen at the back. How different is it? Like relative to the hydrogen in front. Okay,
Yeah.
it's an angle. It is an angle. If I have this CH3 in front, okay,
Mm-hmm. Yes.
how would theta equal to 0 look like to you?
Oh, if theta equals to 0, I cannot
How would
see
it
it. You will not be able to see
try?
anything.
Can you represent it on the diagram, like how it would look like? Tilt it a little bit sideways. So you say you can't see if they are directly over each other. So I want you to tilt your eye a bit sideways. So if you tilt your eye a bit sideways, then you can see one and the other. But obviously they overlap. But show me on
Yeah.
the show me on the projection how it would look like.
From sideways.
So theta is still 0 where they overlap. But I want you
Yeah.
to draw them as if you are sideways a little bit, so that you
Okay.
can see the one at the back as well.
Okay.
Once you have finished drawing, just show me, and then
Okay.
yep, something like that. But obviously they're not tilted as much. They are
Yeah.
more like you said, they overlap each other. You can't exactly see them. But I'm just tilting my head a little bit sideways so that I can show them on the diagram. Can you see that that is actually, let's say, theta equal to 0, where they overlap each other.
Yeah.
So again, this is theta equal to 0 degrees. Okay?
Yeah.
Happy? All right.
Yeah.
I want you to show me. Can you draw on different diagram the projection when theta equal to 60 degree, and then 120 degree, and 210, 270, and 360.
Sorry, what's that? 50 degrees.
So let me start with HA and HA dash. Okay, I will call this one in front as HA, the one in front as HA, the hydrogen at the back as HA prime or dash, HA prime. Okay, so I want you to draw how the projection would look like when theta equal to 60 degree,
Uh-huh.
how it would look like when it's 60 degree, 120 degree, 180 degree, 240 degree, 300 degree, and 360. So every 60 degree.
Okay.
So draw on separate diagram. Do you understand the question?
Yeah, yeah.
Okay. Keep the one in front as HA being vertical. Just rotate the one at the back.
Yep.
So what we're doing is we are rotating about the carbon-carbon bond. And then draw the different projections.
0 degree.
So I've just drawn 0 degree for you. Maybe you can draw 60 degree for me, and you show me first before you go further.
Okay. Something like that.
Forget about the rest of the labeling. So we started with just that. So you're right, but just label it. Just label one of the one in front as HA, the one at the back as HA prime, so that it's easy. So you don't have to label all of them.
All right.
So something like that. Okay, cool.
Yeah.
So why don't you try 120 degree?
Okay. 120-degree, that would be overlap. Or
That is not 120 degree. Can you just label, like, what I said just now? Can you not label all of the protons? Just label one of it as HA. Keep the rest unlabeled.
oh, no need to write the H.
Yeah, just one of it.
Okay,
So we
okay.
started with one in front as HA. Yeah. And then the one at the back as HA dash. Forget about labeling the rest.
Okay.
So here the HA is still at this position because I don't change it. I rotate the one at the back.
Yeah.
So the one at the back now, this is the HA dash. I don't care about labeling the rest because I'm looking at this.
Yeah.
Now it's 60 degree, which you have gotten correctly already. Can you now draw for me the 120 degree without labeling the rest of it? Because it's quite hard to see what is happening once you label all of them.
Oh, okay.
So there should just be HA, and there should just be one HA prime. The rest is just H.
Okay.
So draw for me again the 120 degree, how it will look like.
60-degree. Okay, how about this?
Yep, that's fine. But can you put the rest of the hydrogen in, but without labeling it as with the subscript? Put the rest of the hydrogen in, but without putting in the subscript A or A prime, just
In,
hydrogen.
or do I have to
Yep,
add?
like that. Yep. But then the one at the back, you only got one hydrogen.
Oh, okay. You want me to add more?
Yeah. The rest of it. So this is what I meant by only label the HA and the H. The rest keep it as hydrogen.
So this would be symmetrical.
So you were right, they overlap, yeah. So
Yeah.
and then so it's kind of similar to when theta equal to 0 degree, they overlap. Hence you have to tilt it a little bit sideways to show it. Can you show me what you've got?
Wait, last one is a bit tricky. Not entirely sure about the bottom one.
Okay, you shouldn't. Again, I mentioned, like, forget about the rest of the level. Okay, you can put down the paper. You can put down the paper. So what I'm saying is, it. Hang on, let me just show you.
Oh,
It's
just
something like that. Okay, so you have noticed that I've drawn the one at the back towards this side rather than this side. It doesn't matter. But as long as if I'm looking at the other angle, if the HA prime is towards that side, then the one at the back must be towards that side a little bit. The one at the back must be towards that side a little bit.
yeah.
I rotate a little bit clockwise. Whereas this one, you will see that it was a little bit anti-clockwise, a little bit anti-clockwise, a little bit anti-clockwise.
Yeah.
It's a matter of perspective, yeah, and it's a question of when you draw it, can you see it or can you not see it? Okay, cool. So again, I just want the label HA and HA prime. The rest is just H. You get it
Okay.
now, yeah?
Yeah,
Okay.
yeah.
So that is theta equal to 120 degree, and then can you draw for me 180 degree, and then 240, and then 300 and 360. Complete the rest. It should be a matter of routine exercise now. So now that you get the hang of it.
Okay. Here is 180 degree.
Nope, there is no 180 degree. Is that 180 degree to you? Where is the no? Have a look on your diagram for the 180 degree. Where is the HA and the HA1? Are they 180 degree to each other?
They are overlapping, right?
So is that 180 degree to each other?
I drew it in a bit from looking at the sideway.
Yeah, but then when they are overlapping to each other, that looks exactly like 0 degree.
Oh, okay.
You got the 120 degree correct already, right? So you rotate clockwise again by 60 degree. How does it look like to you?
Okay.
Even from 120 degree, from 120 degree, if you rotate 60 degree anti-clockwise, you go back to 60. No way you go back to 0 unless somehow your math is incorrect.
Okay.
The theta, think about it, the HA and the HA prime is the angle subtended between them, not
0. Oh, okay.
you keep on rotating them. You see, you keep on rotating them. You rotate them clockwise, keep on rotating them.
Okay.
You gotta be wise to pick up from there. You already messed up on the 60 on the 60 and 120, and now you couldn't get the 180 as well. Show me the 180 first once you got it.
Okay. So HA will go down.
Don't overcomplicate things. Follow your own diagram. Follow your own. Rotate 60 degree, become like that. Rotate further 60 degree and you got 120 degree. Rotate another 60 degree. How does it look like? Thing is, you are not following.
It goes downwards.
Yeah, but that is not exactly 180 degree. That is more like one. That is more like 120 again, because you are showing them as the side way overlapping, aren't they?
Oh.
Look, this is the 180 degree.
Oh, okay.
Totally opposite to each other, isn't it?
Yeah.
What you have drawn is you have drawn them overlapping again like that. That is overlapping. Nowhere 180 degree is overlapping. 180 degree, totally opposite.
Okay.
Projection. Your eye is looking along the carbon projection, and you got one correct, and then somehow you couldn't get the next one, and then you get the next one correct, and somehow you couldn't get the next one. That's your problem. You need to pick up from things like that. You cannot be expect to be told every single way. You rotate another 60 degree, then this will overlap with this. Again, they overlap. When they're in this type of projection, they overlap. What you have drawn is not 180 degree. What you have drawn is them overlapping. Nowhere there is 180 degree. Follow that's why I don't want you to label the rest of it, because once you label the rest of it, you will get confused. You're just following the HA and the HA prime, which you wrote down already, which already been explained to you. Okay, can you draw for me? So that is 180 degree. That's 240 degree. Yeah, 240 degree, because HA is on top. HA is there. HA prime is there. I already gone 60 and then 120. I gone 180 here, and then I rotate another 60 degree, then they overlap again. Can you draw for me 300 degree?
Yeah.
And nope. Your H Did you rotate anti-clockwise or clockwise?
ND.
Throughout just. Oh, you rotate anti-clockwise. Okay, if there is anti-clockwise, that is correct. Yeah, okay. Because it's fine. You can put it. Because I was rotating clockwise. It's fine as long as you rotate it in the same direction. But your 180 degree was definitely wrong because even you rotate clockwise or anti-clockwise, 180 degree, there's got to be like totally opposite each other. Okay, so 300 degree, and then how would the 360 degree look like? Even without drawing, what do you think the 360 degree would look like?
Oh, at the middle. I mean,
Show me. So based on your rotation throughout, you rotate anti-clockwise, that's fine. Whether you rotate anti-clockwise or clockwise is fine, as long as you be consistent. I want to see how it looks like when it's 360 degree.
Wait, sorry. Okay. So 360 should. Oh wait, where is it? It will revert to original position.
Yep, exactly, because 360 degrees is a full cycle, right? So it looks exactly the same as the 0 degree one. When I asked you the first time, even without drawing, you could have told me that, but you told me something else just now. That's why I wanted you to draw it anyway. But again, this kind of thing, pick it up, okay? So I want you to compare your 0 degree and your 60 degree. Okay, so we know that carbon can rotate, as in like you can rotate about carbon single bond. So we know the CH3 and the CH3 they can rotate about each other. Okay, so suppose that we are just fixing the CH3 in front as stationary, which is what we have done, and we rotate the one at the back. We keep on rotating them, changing the angle between the hydrogen at the back and the hydrogen in front. So these are what we call conformation. So things as isomer. Isomer are different. These are not isomers. These are just different configuration that you can get rotating about single bond. This is actually a first year organic chem, which biochemists cover as well. And it's a very simple exercise. That's why they like to ask it in an interview. Okay. The next bit is the harder bit. Okay, it's the more difficult bit. The first bit on drawing this projection is not the harder bit. Okay. So in terms of energy, because you can rotate about in terms of energy, which one do you think is more favored? So for theta equal to 0 degree or 60 degree, which one do you think is a much more stable conformation? So
Unstable.
Which one is more stable based on your structure? When theta equal to 0 degree versus when theta equal to 60 degree. So look at your own diagram. So when it's 0 degree, the hydrogen in front, the hydrogen at the back overlap, right?
Yeah.
Yeah. And then when it's 60 degree, they don't overlap. They are sideways. Yeah.
Yeah.
Okay. So how do they differ in energy? Which one would be more stable in energy, or do they have the same energy actually?
Wait, which one is 60 degree?
I also don't know. You drew your own 60 degree.
Wait. Oh,
if you are missing it, you can easily draw it again, right? Now that you know how to draw them.
Okay, yeah.
Okay.
Yeah.
So 0 degree compare with 60 degree. Would they be different in energy, or would they have the same energy?
I'm guessing there will be a difference.
Why do you think there's a difference? And if there's a difference, which one do you think will be higher? Which one do you think will be lower, and why?
Okay. The what do you call that? The 60 degree will be more stable.
The what? Which one is more stable?
60 degree.
Why is that?
Because the hydrogens are rather to be, I mean, because they are repelled, they try to be further as possible from each other, so they they reach a 60-degree angle.
Why do they repel? Why do they repel?
Because both of them are delta positive charged. So
Yeah, but we are talking about carbon hydrogen, and the hydrogen only has one electron, and the electron is already inside the covalent bond. We don't normally, in fact, we don't call CH as delta plus hydrogen at all, because it's almost not delta plus, it's almost non-polar at all. Okay, because there's nothing else there. All right. And the CH bond is quite strong as well. So no matter how polarized it is, it doesn't break that easily. Okay. But you're right, they do repel, and it's a matter of electronic orbitals. Yeah, okay. They occupy space. So when it's 0 degree, when we keep on talking about these overlapping things, right? They don't actually overlap. It's just that your projection looks like they are stacking on top of each other. So that kind of projection is called eclipse. Eclipse. You know what's an eclipse? Okay, it's called an eclipse with a ed at the end. It's an
yeah,
eclipse conformation. And then the one where it's sideway like 60 degree, or when it's 180 degree, and also when it was 300 degree. Okay, that's when they are like quite far apart from each other, right? They are quite happily being in that state. That is called a staggered because they are sideways, staggered sideways. Staggered. Okay, eclipse and staggered. I will use this term later on in our second part of the discussion. Okay, so what you're saying is that the staggered conformation is energetically more favorable than the eclipse conformation, because the hydrogen, they are as far apart from each other as possible, right? Okay. Now I want you to sketch a graph. Sketch a graph. So they are of different energy.
yeah.
So one of them would have higher energy than the other. Sketch a graph of energy against theta.
Okay.
And theta is the angle between that group in front and the group at the back. So this is an easy model because everything is just hydrogen. Okay. How would the energy changes when theta changes based on whatever you just draw? Do you want me to repeat the question, or you understand what you're supposed to do?
Yeah, I understand.
Okay.
Okay.
Maybe you sketch from 0. So the angle we move altogether is 360 degree. But maybe if
Yeah,
you just show me how it would look like 0 to 60 first.
0 to 60.
Yeah.
Okay.
How would the graph look like?
0.
So we are not concerned about actual value, but we are looking at trends and how it would look like. Don't be too concerned about getting it right, like perfectly right. Let's see just how you're thinking first. Okay,
Oh, where is it?
where's your graph? So you're saying that energy will increase, energy will become more positive when you go from 0 to 60. So in an energy level diagram, in chemistry, when you have a very active intermediate transition state, do they go higher up or do they go lower in energy?
So, sorry, can you
When
repeat?
you have intermediate, or when you have transition state, do they go up in energy or do they go down in energy?
Intermediate.
Yeah, when you have starting material, and
Uh-huh.
then you proceed via an intermediate SN1 reaction,
Oh,
or you proceed via transition state SN2 reaction. Is the energy going up or is the energy going down?
up.
Yeah, because it
Wait.
becomes more unstable, right?
Yeah.
Yeah, and the energy goes up because it gets more and more unstable. You want the energy to be going down and down and down because
Oh,
there's more stable. There's the yeah, okay. If you read the Why Chemical Reactions Happen book, you would know. Okay, so revise your sketch. So you were saying that when theta equal to 60 degrees, is more stable than 0 degree, right? So the
right.
energy should go down because it become more stable. Okay, so it goes down. All right. So what can you say from 60 to 120 degree? How would it look like?
60 to 120.
So when you slowly increase the angle from 60 to 120, looking at your own diagram, you know, the one you just draw, your own work.
Then it should increase again.
Show me on your diagram.
Okay.
Okay, so now it's going to eclipse again the energy. So why have you drawn the energy as 0? The energy is just an arbitrary value. Yeah, it might be 0, it might be something else, but just leave it as energy. We don't care about the 0 thing because we don't know about absolute value. But what is interesting, if you have put them at the same level, why do you think they're of the same level as 0 degree? Could it be higher? Could it be lower than when theta equal to 0? Why? You started with the energy when theta equal to 0, and then you ended up drawing at the same level when theta equal to 120 degrees. Is there a reason why you did that?
Because for 0 degrees and 120 degrees it's slightly different. I mean, one is clockwise, one is anti-clockwise.
Then why is the energy the same? But you have drawn them to be the same. Are they the same? Are they the same conformation, statistically speaking?
No.
But are all hydrogen?
What's that? Sorry?
Are all of these hydrogen atoms that you are moving around, are any of them different? They are all hydrogen, right?
Yeah.
So the fact that when you have the eclipse, whether it's eclipse in 0 degree or whether you have them eclipse at 120 degree, is it still the same hydrogen atom that's in front and at the back?
Yeah.
So statistically speaking, are they statistically the same or different?
The same.
So should the energy statistically be different or the same?
The same.
Yeah, then it doesn't matter clockwise or anti-clockwise as long as they're eclipsed, because what you have is a very simple system. Everything is just hydrogen. When everything is hydrogen over against hydrogen, statistically speaking, when 0 degree and 180 degree is exactly the same. Even when 240 degrees is exactly the same. That's how you know. And then when they are staggered at 60 degree or when they are staggered at 180 degree, you will draw them and then you realize that all of them are exactly hydrogen atoms. They are all 60 degree to each other. When they are staggered, they are 60 degree to each other exactly. And there's when you reach the minimal energy and you know they are all the same level. So there's only one minimum, one maximum, and they are the same value.
Yeah.
Do you get it now? Do you want to
Yeah.
complete the rest of the curve for me, like how the energy will vary from 0 to 360 degree? Now that we have established these statistics.
I'll draw a new graph. Doesn't fit.
Really, you just continue the graph. Anyway, do whatever you want. Just show me.
Okay.
It's a sketch.
By the looks of it, it's a sine graph. Yeah, sorry, it's messy.
Hang on. No. Why is the angle at 0 degree different from the? I see. Why is the value of energy different at 0 degree at the other? Can you show me the diagram again? You have just deduced that it's a sine graph just like that, but it's not supposed to be anything except that what we just established is when they are staggered, there is one energy. It's called Emax. Let's call it Emax. And Emax is the same whether it's staggered at 0 degree or whether it's staggered at 120 degree or whether it's staggered 240 degree. Sorry, I mean eclipse at 0 degree, 120 degree, or 240 degree. Show me your graph again, and I'll tell you where you're gone wrong. Show me again your graph. Oh, I can't see a graph. What you have drawn is completely wrong, man. You started out okay just now, and then you ended up messing with it. Okay, you can put down your graph now. So you have your energy at 180 degree is different from the energy at 0 degree, and you don't understand 180 degree. 180 degree just now your own was staggered. How can staggered be maximum? Look at your own diagram. 180 degree. Where is your 180 degree?
Oh, it's the same as.
Yeah, it's minimal, right? Because it's minimal repulsion. It has to be E minimum. You have just randomly established that it's a sine curve because you decide to be a mathematician and suddenly decide like that. Okay, let me just draw this for you.
Okay.
So when 0 degree, you have E maximum. So I'll call it E maximum. And then there's an E minimum. I will set out the curve like that. I have an energy. I have an angle, 0 degree. At 0 degree is eclipse. So is it E max or E min?
What's that? Oh,
At 0
Emax.
degree, you will have E max, right? Because they're eclipse. Easy.
Yeah.
At 60 degree, do you have E max or E min? E min. At 120 degree, do you have E max or E min? It
Emax.
oscillates, right? Okay, so it goes up to max again because at 120 degree, it's eclipse again. And then at 180 degree, it goes back to E min. So what you have is, I don't care like that, something like that. You're right, it's oscillation. But I don't know whether it's a sine or a cosine because I am not fixated. I am not fixated on where to put the axis because there's no absolute value. What I've done is look at the on diagram. Listen to your explanation again on which conformation has what and what mistake. And from there onwards, you can understand. You are more fixated on just putting a number to it, but there's no such thing. You need to relate it to the chemistry. You are doing chemistry based on the maths. You're doing biochemistry based on maths. You're not doing maths based on chemistry. Okay? Anyway, let's move on to a more complicated thing. So you got the hang of it already, right? You got the hang of it already. This is a more complicated thing. Do it for butane. Start fresh. Do it for butane. So with butane, what I want you to do is look along the central 2 carbon. I want you to look at the terminal 2 carbon. So butane has 4 carbon. Look along the central 2 carbon. We are looking at straight chain butane.
Yeah.
4 carbon, right? Butane has 4 carbon, right?
Yep. Yeah.
Your eye is looking along the carbon 2 and carbon 3. How would it look like? 0 degree to draw for me for 0 degree. How would it look like? Butane. How is butane different from ethane? That's your biggest challenge right now. Draw for me 0 degree. How would it look like? I want the 0 degree to be the CH3 eclipse.
What's that?
I want the 2 CH3 to be eclipsed together at 0 degree.
Oh.
You know what is butane, right?
Yeah,
butane and 2 central carbon, and then it got a CH3 in front, it's got a CH3 at the back because there's your carbon 1 and your carbon 4.
Okay.
You alright? Or maybe it will help if you draw a straight chain butane and then you have your eye looking across the C2 and C3 and then you project it onto the diagram that we just draw for ethane just now and see if it helps or not.
What's that?
Okay, let me draw for you butane. This is 2, 3, 4 carbon. Okay? Now,
Bent it.
what I want is, I want my eye to be looking at. I want my eye to be looking at C2 and C3.
Okay.
So now, I would have projection diagram.
Yeah.
The one in front, let's say, is C2. Yeah.
Yeah.
So, okay, so this is C2. Where is C2 connected to? C2 is connected to C1. So if this is C1, what does C1 have? C1 have a CH3.
Yeah.
So I have a CH3. Can you
Yeah.
then, right? Butane.
Yeah.
So on the other two side, what is here? So this is carbon 2. This is carbon 2. Carbon 2 is bonded to carbon 1, which is what is on the other two side of carbon 2? What else is on carbon 2?
Hydrogen.
Yeah, 2 hydrogen.
Yeah. 2 hydrogen.
When you are looking along carbon 2, here is the criteria. I'll show 0 degree for you, and then you can move on from there.
Okay.
I will establish the eclipse position as the zero as a theta equal to 0 degree. It doesn't matter what you establish, but I choose to establish this as 0 degree.
Yeah.
The C2 is connected to C3 at the back. The C3 at the back is connected to C4. Can you see that? This is C4. C1, C2. Your
Yeah.
eye along C2 and C3. Yeah?
Yeah.
So what is at the back? The back is C3. What is C3 connected to? C3 is connected to C4. What is C4? C4 is the CH3. What else is on carbon 3? What else is on C3? This carbon 3 has one covalent bond, two
Hydrogen.
covalent bonds. Sorry?
And hydrogens.
There
Yeah.
should be 2 hydrogen, okay? This is an eclipse position. Can you follow?
Wait.
This
The
is
one that the one at the back is C4, right?
doesn't matter, it could be C1, but yep.
Yeah. Okay.
On your carbon, can you see 4 carbon now?
Yeah.
In the
One.
middle are 2 carbon. You are looking along the middle 2 carbon.
Yeah.
4 carbon, right?
Yeah.
Okay. Theta equal to 0 degree. Straight away from ethane to butane, there's an increased difficulty already. Yeah? I haven't even moved on to hexane yet.
Okay. 0 degree.
Theta equal to 0. Same idea. Happy so far?
Yeah.
How would it look like when it's 60 degree, 120 degree, 180 degree, 240 degree, 300 degree, 360 degree? Your final task, why you draw all of them, is so that you can see and sketch out energy against theta for butane. That's the task actually. But to complete the task, it will make your life easier if you draw out each of the conformation for the angle. Then it will be able to sketch the diagram. You want me to repeat anything?
No. I'll try first.
So we are looking at butane right now, yeah? Butane. And you are looking along the middle 2 carbon. Show me when you have done 60 degree and 120 degree. I just want to see what it's like.
Wait, 60 first.
So you are rotating it anti-clockwise, right? Okay, cool. That's fine. 60 degrees, correct? Yep. It's easy now because instead of labeling A and B, because A and B just now is because you have just everything hydrogen. Now it's easy because you can just follow the CH3. Okay, so no need to label them. So I trust you can do the 120 degree. So convince yourself, just draw all of them: 120 degree, 180, 240, 300, 360. And then once you've done all of them, sketch the graph for me. Energy against theta.
You want to see the drawing first?
Have you gotten all the diagrams?
Yeah.
Show me. 60, and then when they want at 20, lift up a little bit. Lift up a little bit. Yeah, 180 is when they are totally opposite each other. 240, back to that, and then 300, and then 360. Your 360 look very much like... No, your 360 is wrong, man. Your 360 is wrong. Can you draw your 360 again?
Okay.
Follow from your 270. Follow from your 240. From your 300. Sorry. Follow for your 300, and then draw the 360 degree.
Yeah.
Your 360 degree one is extremely wrong. Although it should look like the 0 degree essentially. Because it's one full cycle, right? Do you get where you went wrong?
Yeah.
You know it's going to look like exactly like 0 degree. Then how in the world do you get that? I also don't. Okay, you know it's supposed to look like 0 degree because it goes back one full cycle, 360 degree, right?
Oh, okay. Yeah.
Okay, so your previous diagram was wrong. Yeah, now it's fine. So it's staggered. It's eclipse again. Yeah. Okay, cool. Do you think before you go to the energy diagram, do you think the diagram is gonna look exactly the same as the E10?
I don't think so because in this case,
Huh?
because in this case the position is different. The
Position of what? What is different?
this time there is CH3, so it makes a difference. It's not the same as.
How is it different? Like, how would it be different? Do you mind like putting it into words for me, or would it be easier for you to draw it out?
Because like the carbon now it's the other carbon, the carbon 3, right? Yeah, the
So
carbon.
let's just know your 2 and 3 are in the middle. They are
Yeah.
not your carbon 3. Let's just talk about carbon. Carbon 1 is the one in front, carbon 4 is the one at the back. Is 1 and 4. 2 and 3 are in the middle.
So the carbon
Okay.
4, it will be in different position for each of the different
Okay.
angles, aside from
Okay.
360.
Okay. So it's best to talk about energy. Okay.
Yeah.
Let's just give a value. Let's just give a value. Let's just start with do you think when they are eclipsed, do you think when theta equal to 0, when they're eclipsed like that, out of all the conformation, in fact, any of the theta, out of all the conformation, which one do you think is the highest in energy? Is the most unstable? Is the least favored? Which one do you think is the least favored? Basically, which one will have the highest energy? Which one is the least stable?
0, 360. Wait. And also, what's this? Wait. Yeah, 0 and 360 only, I think.
Okay, so you think that is your Emax. Okay.
Yeah.
Let's think about the other end of the scale. Which one do you think is going to have the minimal energy?
Minimal energy, 180 degrees.
Anything else?
No, that's all. 180.
So all you have given me is 0 degree, 180, and 360, whereas we still have 60, 120, we have 240, and we have 300 degree.
Yeah.
So you are saying that these angles, like the energy at these particular angles, they don't fit the Emax or Emin. Where do they fit then?
In the middle of those.
Okay, in the middle. So let's say we have how would we label it? Let's label the one in the middle as how would you like to label the one in the middle? Give me a yeah. Tell me how would you like to label the one in the middle? So we have Emax and Emin. So
Yeah.
how would you like to label the one in the middle? So if you say they are in the middle,
Yeah.
that means there's another Emin and there's another Emax, right?
Yeah.
So let's call it Emin number 2 and Emax number 2.
Yeah.
So the first one was 1 and 1. Okay. So which one would so we know the minimum energy you said just now, the most minimum was 180 degree. So which one would be above 180 degree?
Meaning more
Would
unstable.
would all the four angles give you the same energy?
No.
If not, then how would you decide?
We are looking at the distance between the two carbons, so
We are not looking at the distance.
I mean
We're looking at the extent of repulsion. Okay, we're looking at the extent of repulsion. CS3 is a much bigger group, so they're bound to repel. Anyway, continue.
So 60 and 120 is above.
Sorry?
60 and 120 is above.
60 and 120. So you have decided that 60 and 120
It's more
is different energy than 240 and 300. That's what you're saying?
yeah.
Okay. So between these two different levels, which one will be higher in energy and which one will be lower?
Which one? 60 and 120.
So you have two set now, right? So you have divided them into two set. You have gotten 60 degree and you have gotten 50 degree together, and you have also gotten 240 and 300 degree together. So between these two sets, which set will have higher energy and which set will have lower energy?
60 and 120 will have higher energy.
So that will be Emax 2. That's what you're saying, right?
Yeah.
Okay. So therefore, they will put the 240 and 300 degrees Celsius as a minimum number 2. Okay. Given all this information, can you now plot a graph of energy against theta for butane? How would the energy changes?
60. So 0 and 360 are the maximum. 180 is minimum.
Actually, before you continue, so you're right, the 180 degrees is minimum and maximum was 0 and 360. So that was what we established before, right? Okay. And you said like 60 degree and 120 degree belong as a set.
Yeah.
Okay. Can you look at your conformation diagram, your projection diagram for 60 degree and 120 degree? Is one of them eclipse or are both of them staggered?
60 and 120.
Yeah.
One of them is eclipse. The
One of them is eclipse, right? So
yeah.
if one of them is eclipse and one of them is staggered, can they have the same energy? When they're eclipse, they are totally overlapping, one on top of each other, right? Can they
Yeah.
have the same energy when they are eclipse? And then the other one being staggered?
No.
So should 60 degree and 120 degree belong as a set?
No.
So do you want to revise your set again? Because you weren't thinking right the first time.
Here's my graph anyways, though.
So what you have got is okay. But then you have you should probably revise the section where we talk about the stagger and the eclipse for 60 and 120 degree. So you know the 60 and 120 degree, right? So if one is staggered and one is eclipse, one of them is more unstable than the other.
Yeah.
So it won't continuously go down, by the way. It will not. So what will happen?
From 60 to 1. So
Yeah,
60,
from 60 to 120.
so 60 is staggered. 120 is eclipse.
Yeah, but the eclipse is CH3 and H, whereas the eclipse at 0 degree and 360 is CH3 and CH3. So that is the energy maximum. So we have established that.
Oh.
So what I'm saying is your sketch is incorrect because your idea from 60 degree to 120 degree was incorrect.
Yeah.
So now that we have established where you went wrong, so do you want to revise your sketch or?
Sure. Sorry. So eclipse will be is most unstable. Wait. Yeah. Okay.
Up, down, increase a little bit, go down again, increase a little bit. That is perfect. That is exactly what it's like. Okay. I'm just going to send you I'll send you. No, actually, you can Google this. Are you on your computer right now?
Yeah. Yeah.
Okay. Can you Google for me butane conformer conformer energy, and then go for images. Instead of Google, you just click on the images.
Yeah, I can see it.
You see that the shape of the graph?
Yeah.
You see the graph is exactly what you have drawn? It's
Yeah.
kind of similar. Okay, so basically there are two minimal energy and there are two maximum energy. So it's slightly different from the ethane one, where because everything is just hydrogen, is very simple. And then I can go on and build the complexity with an ethyl group. But you can imagine that if you have a hexane molecule, then what you have is a CH3 CH2 instead of CH3, and it's gonna look almost similar to butane but slightly different, because then instead of just the CH3, you also have the CH2 and the CH3, and you can rotate about the carbon bond there. That's why, like, when you have hexane, it's a lot more complicated.
Yeah.
All right, but butane is probably as far as they will go in terms of complexity. So what have we done today? We have talked a very simple thing. The projection diagram is a Newman projection diagram, but it's just a projection diagram viewing along the carbon. Okay, you started out quite badly in the sense that you are not comfortable with this chemistry because it's not your A-level chemistry, and in pure sense, it's not an A-level chemistry, but it's a very simple chemistry. It's just thinking about, like, you can rotate about single bond, you cannot rotate about double bond. When you rotate about single bond, they have slightly different energy. And we talk about energy maxima and energy minima because when they are eclipsed, like groups or atoms, they repel each other because they like to occupy. What you don't realize is that atoms occupy space in 3 dimensions. Okay, and then the butane is obviously the slightly more difficult example, but I think you did the butane better than you did the ethane actually. But that's great because you are used to it now. I mean, after an hour, if you're still not used to the idea, I'm gonna kill you. Okay. But yeah, hopefully you get the idea that you can pick things up along the way, and you need to pick things up very quickly along the way. So interview is a chance for the tutors to decide, are you the type of person who can survive the rigorous tutorial procedure we have in Oxford or not? So it's a matter of, are you a fast learner? Can you pick things up from where you make a mistake or not? Or are you the type to linger around and wait for stuff to happen? Okay, cool. I will talk to you more if we get an interview invitation after your exam finish. All right. In any sense, yeah, I mean your UCAS is done already, right?
Yeah.
Get it sent off before the 15th, yeah, so that you don't have anything to worry about by the time exam starts. Okay, cool. Sorry,
I already sent it off.
Oh, you already sent it off. Cool. As long as everything is checked by Charles, then you should be okay. Did you settle for Auckland College? Auckland, right? The college that you applied to, Auckland, yeah. Okay. Yeah, there's a very academic and competitive college, but hopefully they'll give you a chance. Okay, cool. All right, good luck for your exams. Any question for me?
No.
I've got one simple question for you. Name me some Nobel Prize winner in. Is there a Nobel Prize for biology? That's my question.
Biology.
This Nobel Prize for biology.
Yeah.
No.
Yeah. There was.
There isn't. There's not an area. Look it up. There's no such thing as Nobel Prize in biology.
Oh.
Just like there's no Nobel Prize for maths. Oh, there's Nobel Prize for physiology and medicine, but not for biology.
Oh, the DNA is not counted as biology.
What they got the DNA for? Do you know what category was that for? No. That is for getting the crystal structure of DNA. That's for getting the crystal structure of DNA, which is a protein structure, right? So you can get crystal structure of proteins. You can get crystal structure of ribosome, insulin, DNA. What else? Insulin, myoglobin, hemoglobin. They are all crystal structures. Each of them has won Nobel Prize in the past 50 years or so. That's because crystallography is very important. You get to see the picture, what atoms are bonded to what atom. You get bond length and bond angles. And insulin is very important because if we know the structure, we can make it. If we can make it, you don't have to rely on the natural source of insulin, which is from where? Where's the natural source of insulin from?
The pancreas, the beta cells of the pancreas.
Okay,
Islet cells.
so back in the days, back in the past, if someone doesn't have insulin, where did they get the insulin from?
Animals.
Like if someone is diabetic, I mean
Yeah.
animals, right? Okay. So these days you don't get the insulin from animals anymore because there's only so many animals you can get the pancreas from. Plus there are also religious reason for not getting the stuff from certain as well. Okay. So you can make insulin by synthetic chemists these days because you know the structure, you know what it looks like. Okay.
Yeah.
There's no Nobel Prize for chemistry, but there's quite a lot of Nobel Prize for biochemistry. Because it's the interface between biological science and chemistry, and because there's no Nobel Prize for biology itself, so a lot of biologists also won the Nobel Prize for other categories like for chemistry or under medicine. Okay, but DNA was under the chemistry category. Who discovered DNA? Who discovered the structure of DNA?
I forgot. There's two people. There was two people.
Three actually.
I
There are three actually. But the two that you learn, they are Francis Clark and
don't remember.
I also forgot their name already. James something.
James Watson.
James Watson, yeah. So there's a laboratory in Cambridge, University of Cambridge, named after him, because both of them were from Cambridge, and both of them were male. And the story was Dorothy Hodgkin, who was a chemistry crystallographer from Oxford at the time. So she actually got the crystal structure of DNA first. Then she invited them to Oxford to have a look at the structure, and then they submitted the paper without her name. So those two got credited, and Dorothy Hodgkin didn't get a Nobel Prize for DNA.
Oh.
But Dorothy Hodgkin got a Nobel Prize in the end in chemistry for structure of insulin. So she is a crystallographer. So she can. Back then, there's no computer. She has to do it manually.
Yeah.
A lot of work. Like I think it was like 2 years or 3 years of work, just going through the calculations and getting the structure of insulin correct. So she got a Nobel Prize for crystal of insulin in the end. So she is a crystallographer. But yeah, Dorothy Hodgkin was at Oxford. Who else you know won a Nobel Prize? What is this year Nobel Prize in chemistry for?
I didn't follow that.
Oh, you didn't follow that. You should have science heroes. You know, like I was just asking a brother yesterday as well. Like you know, when you follow friends and stuff, but like, do you know what's happening in the scientific world? Not just for your personal statement. You know, these are general readings. So this is the difference. Are you just naturally interested in this thing, or are you just interested because it's a okay? There's a context of everything that you're learning. There's a context and there's a reason for it. Okay. But yeah, I mean, there are a lot of important discoveries in biological sciences and also in biochemistry. But all the Nobel Prize mostly is for biophysics or biochemistry, never for pure biology, unfortunately, because sometimes they come under a Nobel Prize in medicine and physiology. So that's where the biologists can get the Nobel Prize for as well. But yeah, I mean, that's really could just read out on those things. They are quite important discovery actually. Okay, like the DNA structure. Yeah, James Watson and Francis Clark should know that you certainly know a few important discovery, but you just never bother to find out who and why and stuff. Okay. All right, I'll leave it there. I'm tired as well. I hope you enjoy your session. Good luck for your exams, and let me know if you hear anything from your college, whether it's rejection or interview. Just let me know. Okay. In the meantime, just focus on exam. Yeah. All right.
Thank you, sir.
Bye bye.